they have a grid tied to them, so they can actually purchase the electricity from these things and resell it cheaper than they could for shoveling coal to do it. And I wanted to make something, like I said, that was ecologically friendly, that when I talked to Portland General Electric about it, they were very concerned about the materials. Well, what kind of materials? We're going to let you in our rivers in Oregon. What are the materials out of? What do you want me to make it out of? I'll make it out of Play-Doh if you want it out of Play-Doh, which is what they wanted to hear. Instead of coming up saying, this is my design and this is what it does and you don't have a choice about it, I said, I could make them out of aluminum, fiberglass. They have to be strong, though. The model you see sitting here in full scale weighs in excess of 200 tons.
I was going to ask you, how big is it in full scale?
Well, I happen to have here, I have this dump truck is about the same scale as that model.
Okay, so if you can envision that dump truck sitting next to this model, then that's how big it would be in real life.
In reality, I also have a model of my son he's a soldier in the U.S. Army, and this is probably closer to scale for what it is.
Okay.
To give you an idea of a scuba diver could work on this thing quite easily. These things are very large, and they're designed that way to take a lot of people concerned about river impact, which turbines have a hard time with if brush or debris or sometimes whole floating trees come running down. Bounce off it and laugh. These things don't care. They don't care if a barge hits it. They don't care.
Are the rivers typically deep enough around a coal plant to accommodate this?
As I said, there are over 600 in the United States, of which about 500 would be applicable for this technology. If you wanted to maintain water navigation, which is kind of important, I really wanted something that the people who own the river, like Kentucky owns the Ohio River, and they use it for navigation a lot, moving barges and things like that. I didn't want to do something that says, but wait a minute, you're going to restrict our navigation. So I wanted something that operates well below, surface traffic. And to me, it was also important. A lot of people have asked, well, why don't you just put it above the water like a big paddle wheel? I wanted something that worked if the river freezes or the tornadoes come through or if hurricanes come ashore. It doesn't matter because they're completely submerged. They're more or less impervious to the weather. I want them to turn 24/7. Okay.
And the river current's what turns them, and so they just constantly run forever. I guess
They're quite simple in the way they are designed to be deployed. You start about a mile or two upriver from an access point like a coal plant or a nuclear plant. You start deploying them over a series of years. Now, it would take 20 or 30 years to really seriously make a dent in the U.S. grid system if you were attaching to the coal, but that's still a relatively long-range plan, but it's worth pursuing. If you wanted to use these strictly on coal plants, if you just wanted to wire them to the 500 coal plants, and you wanted to do it in 30 years, you'd have to build almost 40,000 of these devices. That's over 1,000 a year, which is 3 to 5 a day, which is a massive amount of steel. The steel industry would love these things. Oh my gosh, you'd be building these things forever. You couldn't export them either.
There's some economic benefit over there.
Seriously economic.
Yeah.
And you'd build them close by, and you'd put them on a river barge. You would deploy them with the river barge, the same technology we use to put bridges together. And you'd come ashore and get the next one, assemble it on the barge, train the parts in, take it ashore, take it off, deploy it. You'd have a sensor about a mile or two upstream that would sense that if the river's picking up due to flooding or something, you could regulate the generators to keep the speed constant, which makes it a very low-cost generator. Wind turbines have that difficulty because they can't maintain a constant speed head. Their generators are very expensive and very limited as to how slow or how fast they can go, where these, on the other hand, I can maintain a constant RPM, very good, which makes a very robust industrial-strength commercial generator, very plausible for something like this, which is one of its attributes. I didn't want to invent any new technology, so to speak, that required us to reinvent the wheel. These are just tried and true, steel and dynamics that make this thing work. So I employ America.
Is it feasible to build enough to make a serious impact? I mean, you mentioned you'd have to build 3 to 5 a day. Is that what you said?
That's kind of one of the aspects about working with this design is that I'm not worried about keeping it because no one company in the world could keep this. The biggest company in the world couldn't build 10% of this market worldwide. Besides using them just in U.S. rivers, you can use them along the Florida coast because they make great current generators as well. They work in any current, slow current. They work in tidal flow because they rotate in only one direction, whichever direction you want them to, no matter which way the tidal works. So when you look at the economic analysis of it, at about $10 million a piece, do the math. If you had to make 30,000 of these things,
right,
that's like $300 billion or
right,
something.
Right.
No one company in the world can do it. So
right.
we would end up probably going to each and every company in every part of the U.S. Like, for instance, we talked to Cascade Pump, which is a big company in Santa Fe. He's very interested in making these things. And he may make one kind of to his design. He may actually get some intellectual patents on it, on his design for
right.
a better cup or a better wheel. And then we'd go to like Alstom or GE or Fluor or Pactel, some of the really big people that make power plants, and say, this is our idea. How would you make it? And if you were to make it, and that way, I'm not looking to corner the market with anybody, because you couldn't build enough of these things.
What is the significance of the cup design here on the, like right in here?
This design, we're using it right now as a for FEA finite modeling analysis design, and this is just right at this point in time a hemisphere, and I can get the form drag coefficients for a hemisphere. There's a variety of publications, and I've gone a lot to the U.S. Navy work on hydrokinetics and what it takes to move a submarine through water, and there's a variety of shapes, kind of like a wing, that you could probably adjust to increase the power efficiency of it. But right now, it's just easy enough to do it with these, because we know what these numbers are. Mm-hmm. And so we can stick this in the equation, and we've asked it, so what if I keep the cups out, and I keep the cups out like a wind anerometer? What if I were just to keep the cups out? What kind of power cut I expect between the difference in form drag on this side versus the form drag on that side? And it's pretty decent. It's not as good as it could be. Mm-hmm. And then I can ask the computer, what if I simply fold them up? What if I fold them up? Well, the power really goes very well. More specific, your question is, though, is while a cup produces a certain amount of drag, a different shape may produce a better one, but I'm very concerned about what the drag looks like on this side, because if the current's coming this way, it's pushing it this way, then this is providing drag, and if I can minimize this and maximize this, I can get closer to, on paper, you could probably get closer to 85% efficiency on that design.
So does it turn both ways?
You would just simply flip the head over. You would you would pick out a spot in the river to say, if you're like near a bow of a river, and the current's faster on the outside, you would put this side on the outside. But the one next to it, if the bow goes the other way, the head may be on upside down, and the cups may be on that side, floating the other way. So you can rotate them either direction. Kind of like ducks, you can put them in a line to take advantage of the current.
You really picked a good town to come to talk about this, because there are thousands of engineers right here in Tullahoma, Tennessee. I am not one of those, and but I'm sure they're going to see this and be fascinated with this whole concept here. But are you telling me that through calculations and your skills as an engineer and others that have had input into this, that you're pretty confident this will work?
Very confident.
Yeah.
And my job at the company I do for is to build very large dynamometers, which measure power. Mm-hmm. And I'm talking in excess of 6,000 RPM, 2,000 horsepower, some dynamometers as big as your studio here. I'm not kidding. Uh-huh. Ones that you don't even be in the room when you turn those things on. Right. To large pieces of power transmission components, which we design. And to design this, I just thought along the same line. I asked myself, if I was going to design a dynamometer to measure river current at slow speeds, what would it look like? And how would I use it, and how would I make sure the weather doesn't bother it? And then what do I use for the brake? How would I, to measure power, you have to brake against it, and that's what a dynamometer does. I would just use generators, because that's what we use in our lab. Most of our very large horsepower dynamometers actually have regenerative generators as the braking mechanism. We pump 90% of the power in back onto the grid, because if we didn't, all the lights would go out in the town. We turn those things on, they're horrible. Right. So what happens is this thing is basically designed to act as a river current dynamometer. It just measures the current flow. And the more slippery I make the head on one side and the more powerful I make the header side, the more I am closer to getting true 100% current. And these things operate near 100% current speed, which is, this one particular here was designed to put out about 8 megawatts and about 13 knots of current, which is not a lot. That's about as fast as you walk.